So I'm Chris Hopkin. I'm the CTO and product manager for Battlesnake. Who is familiar with what Battlesnake is or has ever participated? That is amazing. That's way more than I was expecting. Who is registered and planning to go to the event on the 15th? Also awesome. So for those that don't know, Battlesnake is a programming competition event that we run every year in Victoria. It's currently now a separate entity. It used to be part of Dispatch. Now it runs on its own, and we're actually expanding it out to run events online, like we did with the Battlesnake Winter Classic, running off Twitch. And we're looking to actually expand and move into Toronto, Waterloo, possibly down to the US this year, running all these kinds of events where people can come in, do a big hack day to create interesting AIs that play the game Snake, which you will see Jonathan and Xavier talk about in a second. The company's, or the organization's been around for about 5 years. This will be our 6th Battlesnake that we've run. The first one was done in the old Tectoria, it wasn't even called Tectoria then, with the old Viatech workspace. We did it in Ubik for a while, and now we do it at the conference center. Last year had about 1,000 people show up, spectators, devs, friends, all sorts of things. And this year, we're hoping to reach those heights again. We have upwards of 20 sponsors, including our presenters tonight. AWS, they are presenting sponsor, coming out to showcase some of the very cool things that they've done tinkering around with our platform. And we were lucky enough to be invited to come down to reInvent in Las Vegas in December, hang out with Jonathan and Xavier, and sort of talk up both Battlesnake as well as this cool thing that you're about to see. So I'm around for afterwards if you have any questions about Battlesnake or the event. But yeah, so big thing is like we're still taking registration, still open if you want to come in, whether you want to spectate, meet some of the companies involved, or come in for the hack day and participate at different levels, build your own snake, whether it's a machine learning snake or just a straight like if then else AI snake. All of it'll work, it'll be great. But so I'll introduce Xavier and Jonathan, and they'll talk about this, which is amazing.
Thank you, Chris. So my name is Xavier Raffin. I'm a solution architect at AWS Vancouver, and I'm today speaking with Jonathan. Want to introduce yourself?
So I'm an applied scientist in AWS Vancouver as well.
Yeah. So we were talking about a project we are about to open source publicly on the AWS Lab GitHub account. And this is a reinforcement environment for Battlesnake. And the role we had together, so we built that together, and Jonathan is a scientist. He was doing more of the design of the algorithm itself, design the training, the environment, so he will focus on that, where I focused on the infrastructure aspect of it, and the automation, as well as the SageMaker framework that hosts the system. So this is how we split the work, and this is how we will split the presentation. So I saw a lot of hands up when Chris asked who knows Battlesnake, but maybe in case there is some of you that don't know what Battlesnake is. So Battlesnake is a game based on the old phone game named Snake. So the snake will move on the screen, he eats some food, and when he eats food, he becomes longer. And when he eats a wall or his own body, he dies, and the game was about to survive the longest as possible on the screen. And Battlesnake is a new version of it, where there is several snakes on the same screen at the same time, instead of just one. And what makes Battlesnake special is not video game, it's an AI competition platform, so every snakes are controlled by an AI from a different team. So the way it works is that the game engine will call all the AI, so the AI will register for a game to the game engine. They will have all a URL, an HTTP URL to call. For every step, every movement of the snakes, the game engine will call all the snakes submitting the game state and ask for the next move to make. Up, down, left, right. So in terms of specific rules for Battlesnake, because it's a multiplayer version of it, sometimes two snakes can collide head-to-head. If that happens, the longest snake will survive and the shortest will die. If they are about the same length, both die. Okay? Also, there is a starvation mechanism, so you can't avoid food most of the time, and you can't just spin like that forever, because every turn you will lose one life. Your health will reduce, and if you have to eat food to restore your health. Okay. All right.
Okay, so what I'm going to tell you about is the Battlesnake starter pack that we developed. So what we try to do is to hope that all sorts of developers can use it. If you're a reinforcement learning expert, or even if you just want to try to learn how to use reinforcement learning, or maybe you just want to develop your if-else statements, I believe that everyone can use this platform. So maybe I'll introduce the 3 modules that we described. So firstly, we developed a one-click deploy method. So what we did is you just click one button, we give you the URL, and all you do is put it into the Battlesnake engine. So just very simple. And do you want to demonstrate how we initiate this process?
Maybe you just
Okay. I'll go through all 3 first. So okay. So the second module is the reinforcement learning module. So okay, let's just say if you are reinforcement learning enthusiast and you want to train your own algorithm, so you can use this module. So this module will allow you to automatically train a model, and then once again you can deploy it. So the third module is for someone who maybe you don't want to train a new model, you don't really want to use reinforcement learning, but what we did is we provided you a mechanism that you can develop your if-else statements even on top of the reinforcement learning algorithm. So I'll go into a bit more detail about that one. And firstly, we try to demo the. Yeah, do you have a question?
For someone who uses AWS and does things like makes Lambda functions or whatever,
Yeah.
can you situate what this means in terms of AWS?
We will do that at the end.
Yeah. So what I will do now, I will just show you how works the one-click deployment aspect of it on AWS, and then Jonathan can continue explaining, giving all the other explanation, and I'll wait that it deploys, and I will come back to it and explain you the architecture of it at the end. Okay. So I will switch to the browser. So yeah, I have to move this one all the way with my mouse. Okay. So what's next? I don't see it.
Oh, sorry.
Here.
So basically, we try to resolve all the issues that you have with hosting the snake.
Yeah. So all you will need to deploy the snake is an AWS account. So here I'm logged into the AWS console. So you need to be logged in, and yeah, here is the GitHub project we are about to release. So it is private for now. We will publish this one. So, and within this project, we publish a documentation that explains how to use the module, and the 3 steps we were talking about. We are explaining each of them. And for now, I will use. Sorry. Oh, zoom in maybe. Yeah. Is it better like that? Yeah. Sorry. And on one of the documentation pages, there is cloud formation short links that are doing the one-click deployment. Okay, so these are just URL to your own account. This will work only if you are logged in your browser already on your AWS account. So you click deploy. So there is a choice between 8 regions. You click deploy, and it directs you on your AWS account on the CloudFormation page. So CloudFormation is a service that reads templates that describe an infrastructure and that automatically generate this infrastructure on AWS. Okay, so that's why we are using here. So basically, it's a service that helps you to spin up an infrastructure already defined. In that case, it has been defined by us. Okay, so there is the name of the environment. You can choose whatever. We put a default one. You can customize the color of your snake, the head, the tail, and some other details. But what is important, I mean, you can let everything default. You just accept the permission for the template to generate all the resources, the needed resources, and then you create. Maybe I can zoom in also. Yeah, like that. And then you click Create Step. Okay. So now you see my CloudFormation stack is in status Create in Progress. Within this tab of the events, you can see, if I refresh here, you can see that it is working. It is currently creating multiple resources of the whole architecture needed to deploy the training and the endpoints and so on. So this process takes several minutes. That's why now I will go back to the presentation.
So I'll talk about the reinforcement learning module now. So maybe I'll just describe a bit about reinforcement learning. Has anyone is anyone a reinforcement learning expert here? Not yet, maybe after this talk. Okay, so maybe I'll try to explain a bit about how it works. So I'm not an expert in this field, so please feel free to stop me at any time if you want to. So in reinforcement learning, you have an agent that interacts with the environment. So specifically, the agent provides several actions which changes the state of the environment, and also the environment provides rewards for the actions that it took. So the aim of this process is for the agent to maximize its reward. So maybe, as an example, maybe in self-driving cars, the car would be the agent, and then the agents can have actions, for example, accelerate, decelerate, turn left, turn right. And the environment could be the road, and the agents view the roads in form of images. And the rewards, I think usually they would use the number of kms that the car has driven. So for example, if the car sees that the road is turning to the right, so to maximize the number of kms that you want to drive, the car should also turn right. Okay, so as an example here, so let's just say if the environment shows a stop sign. So you might think that, okay, since the agent is actually trying to maximize its reward, it will just go straight to it, right? But actually, the aim of reinforcement learning is actually to maximize all the future rewards as well. So in fact, stopping at the stop sign will maximize the future rewards, and it should learn how to stop. So maybe another example is AlphaGo. So the agent would decide the positions of each one of the pieces in the next move. The environment would be the positions of each one of these pieces, and the reward is simple, which is just to win or lose. Okay, so how would one do it with Battlesnakes? So what would the actions be?
Move?
Yeah, move.
Up, down.
Yeah, up, down, left, right. Yeah. So what would the environment or the state be? Yeah, position of the snakes. Food. Position of the other snakes, right? Health, good point. I should have added that in. Okay, so what about the reward? Actually, the reward is actually quite complicated, a bit more complicated. So I'll go into that a bit later. But Battlesnake says you have multiple snakes, right? So one would actually have to take care of each one of the snake's action. It's actually also just a direct, it's just a direct extension of the previous case. So this is called a multi-agent reinforcement learning algorithm environment. So for example, like AlphaGo, not AlphaGo, AlphaStar, StarCraft, where each one of the units does its own thing. That's a multi-agent reinforcement learning problem. Yeah.
To be clear, is this a collaborative where you're trying to optimize every snake's movement, or is it adversarial where you would think about your own snake and assume everyone else is the enemy when you say multi-agent?
So how I did it here was that it's kind of each one of the snakes does its own thing, tries to maximize their own reward. Yeah.
So it's like each of the one runs its own reinforcement learning model. It's not a so for StarCraft, you have to manage like 50 units at the same time. They all need to do their own thing.
Yeah, so I believe what they do is they have maybe one network, and then you tell it what unit it is, and then it would just do, the actions are attack and move and whatnot. So I modeled it in a similar way.
Oh, okay, I don't think I was clear with my question, sorry.
What is your...
Well, in StarCraft, all the units move together, they're collaborate as a team to fight the enemy. Do the snakes here all collaborate to survive and eat food, or do they all fight each other?
So it's not collaborative, it's competitive.
Okay.
Yeah. Okay. So so this is in this case, each one of the snakes will provide an action, and then it will interact with the environment, and then the rewards per snake will be provided. So as you said, it's a competitive environment. Okay. So I'll go through a bit about the code. Maybe it'll resonate a bit more. So this is actually, this type of machine reinforcement learning, this type of reinforcement learning is called a deep Q network. And that, I'm not sure if anyone heard of a lot of the Atari games that DeepMind used. And that was their invention. So, so how reinforcement learning works, it's kind of like a simulation. You play the game, you make the agent take many actions. And given the state, you will record what the action is, what happened, what the reward was. So specifically, so you define the total number of games here. So maybe it'll be like 10,000 games. You want the module to play 10,000 games. Then you will obtain the initial state right here. And the condition of each one of the states is that there is an agent alive. So in the case of Battlesnake, it's that the snake is still alive. Okay, so the first part is you want to take the action. So this part is a bit complicated, but what happens at the start is that the agents will actually just randomly take an action. And it's because at the start, the agent actually doesn't really know what's going on yet, so you have to seed it with some actions so that it will, you can record maybe good actions or bad actions. And then, so the next part would be how to get so given the actions, what happens? So you can get the net states out of the environment, and you can get the rewards. And finally, you save all of these, the next state, reward, the actions into a memory. And then your memory will store the actions, and then at the end, so agent.learn, that is when the learning mechanism begins. So let me explain a bit about the else statement here. So what happens here is at the start, the agents will just take random actions. But as the agent learns a bit more, then it will eventually start, you can eventually start to take maybe what the agent thinks that it is the best action. So then, for example, let's just say if the reinforcement agent starts to learn how to move and starts to learn how to avoid the walls, then the snakes will eventually start to grow longer. So this way, you can actually get a more variety of the states, which will allow you to, which will allow the snakes to learn better. So I won't go through this too much, but basically this is just how you would extend this to a multi-agent setting. So the only difference is that you will have to loop through all the agents, and then you will have to loop through all the agents for the actions, and you have to loop through all the agents while you're doing the learning.
So can you run multiple agents at the same time as you train your algorithm?
Yes. Yes.
I have one
Yeah.
question.
Yeah.
What's the EPS variable?
Okay, so
Earnings per share.
okay, so no, it's not. It's not really especially. So basically, EPS is actually just how you describe the proportions of random actions versus when the agent should start to do its own stuff. So usually what happens is that at the start, the proportion is very high. So you mainly take random steps, random actions, I mean, and then eventually, slowly, you will decrease the CPS. Yeah, so, I'm sorry, I didn't go through too much of the details in this, but if you're interested, I can give you more material. Yeah.
I'm not sure this question fits in very well right now, but the perception is that these models are sort of a big black box, or they're deep learning.
Yes.
So the question is, what's the secret sauce? How's my Battlesnake better than someone else's Battlesnake? Do I spend more money on AWS so that to get a better Battlesnake, or is there like some subtle infrastructure changes I can make my model that gives me better performance? What's the secret sauce in this?
That's a very deep question. Maybe the CTO can answer later. Yeah, I'm not sure.
I would say the secret sauce here, what you control is you defining the reward function. If you're good at defining a good reward, then your snake will do better than others. Because here, when the snakes move, most of the time it's meaningless. One action is meaningless. You have to do several moves to have a consequences that is positive or negative. And then, so the reward is a multi-step thing, very complex. There is multiple options in the way you represent the universe and, of it. And I would say this is what makes the difference. And this is what experience in building reinforcement learning algorithm make a difference.
So just to clarify, like, what do you mean by defining rewards? This might be about inexperience showing, but
I will explain that later.
okay.
Just be patient. Okay, so I'll actually explain what Xavier was saying at the start. So how do you describe, how do you model this environment? So what we did was I actually built a OpenAI gym. Has anyone heard of what that is? Yeah, so an OpenAI gym is just a method of simulating your reinforcement learning algorithms. And I modeled that as well as I could with the Battlesnake engine. So so basically what happens is that you give it actions, then it should move all the snakes correctly, and then it will give you a reward that you designed. So I will explain the states of how, at least in this module, how we describe all the snakes. So just say, as an example, this is just the board. This is the food. This is a long snake. These are two snakes. It's a very simple example. So what we did was, So we represented the snakes as with an image. So each agent represents one snake. So let's just say if we have 3 snakes here, so we need 3 agents. So each agent is represented with something like this. So I'll explain this in a bit more detail. So it's kind of like an RGB image. So you have 3 channels, red, green, and blue. And the first one represents the food. Second one represents the snake that that your agent is interested in. The third one represents every other snake. So I'll go into a bit of detail. So the food here is always a 1, and then if there's nothing, it's a 0. So a snake is kind of represented like this. So we put a 5 to represent the head, because we think that the head is actually quite important versus the body. Everything else is a 1. And then similar to the other snakes, you may notice that we put a -1 around the border. So what we did was we kind of expanded the size of the board by 1, just to say, okay, this is the wall. If your snake is close to it, don't go there. Just to give the network a bit more information. So so for the second agent, very naive. So for the second agent, what we did was we just rotate the snakes. So if the second agent is representing the green snake will be put in the middle channel, and then every other snake will be put in the last channel. Same with the blue. Okay, so I will explain a bit about the rewards. We tried to make it as simple as possible for our case. So they get +1 every time they survive. That's it for us. And I'll explain it a bit more detail later. Okay. So the agent. So this is the neural network part. I will try to make it as informative as possible. Basically, the neural network, which is here, which takes the game state that we described just now, and then how do we transform that into the positions? So the input to the neural network will be an RGB image. The output of the neural network will be size 4, and which each one of them represents up, down, left, right for the actions. So here is the up, down, left, right. So basically what you kind of want to do is to maximize the total rewards that if you took up, down, or left, or right. So the neural network predicts the total expected rewards for each one of them. So I just put some random numbers here. So for example, if you have a snake like this, and if you go up, it dies, right? It's just the mechanism of the Battlesnake. So then the total expected reward would be 0. So definitely the neural network should learn that you shouldn't take this move. Okay, so how does the neural network learn? Okay, I tried to.
Sorry, quick question. Do you mean total expected over the course of the entire game?
It should be future.
Okay, so it's sort of predicting how long it's going to live.
Pardon me?
It's kind of an estimate of how long it's going to live?
Yeah. Well, depending on the reward, yeah. So for our reward function, yes.
Yeah.
But let's just say if you take another type of reward, then
Something else.
something else, yeah. Okay, so how does the neural network learn? So let's just say at time equals to 0, you give the state to the neural network, and then it predicted this total expected reward. And you say, let's just say you took to go right. Then you get the new reward, so it didn't die. You get a new reward of 1. And then at time equals to 1, which is the next step, you also get the predicted reward. So basically you run the neural network once, then you run it twice at the next state. So what is the relationship between the predicted reward at time equals to 0 versus the predicted reward at time equals to 1? So maybe this will demonstrate it a bit more. So let's just say your total predicted rewards, this is everything in the future. Then you have it at time equals to 1. But one thing that you know, the difference between these two is actually the new reward that you got just now when you simulated once. So then what you're trying to do is to make the neural network learn that, okay, the difference between this one and this one is actually the new reward, which is kind of explained in this equation. I don't expect anyone to be able to understand this. I don't understand it myself. Yeah. Okay. I directly copied it from Wikipedia. Yeah. Okay. So what you're trying to do here is that your network is trying to learn that there's a difference in the rewards just by the 1. Of course, you're going to do that over multiple steps. So what happens here is that this thing here, this part of the equation describes the difference between the expected value at time equals to 0, time equals to 1. The alpha step here is actually what it's trying to say is that, okay, maybe at this particular action, you want to include this much information into the neural network. And then for this next simulation, you kind of want to do the same. Because if you try to just say, okay, if you try to base the neural network based on just one of the terms, then your network is not going to work very well. Okay. Does that make sense, or is it completely?
Max is over what?
What do you mean?
In the equation, the max you have is over what?
The what?
The maximum?
It's over the different actions.
So for every t, or the max over?
The n actions that you, so up, down, left, right.
Okay, for all portions.
Yes, yes. Yeah.
I'm curious if you're able to talk a little bit about what your motivation was behind choosing a Q-learning based approach as opposed to like a policy gradient or an actor critic model?
Yeah, so from my understanding, a Q learning approach works better with discrete action spaces. That's it. Yeah. Yeah, so there are different types of, for anyone who didn't understand, like, so this is a discrete action space because you just have up, down, left, or right. So for example, in a self-driving car, maybe the amount you turn, that is a continuous action space. So that actually, usually people would use a different class of algorithms for that. Apparently it doesn't work as well for continuous action spaces. Okay, so trying to answer that gentleman's question. So what differentiates between different people's models? Okay, so I kind of suggested a few things that you could try to improve upon. So first one is the environment representation. So basically what we did here was actually quite simple. We just took it as images. But as you can imagine, let's just say if the map size changes, then what? The neural network won't work. No. There are possible methods that you can use to mitigate this issue. For example, like instead of taking the whole state as an image, what you can do is just take the head, figure out the differences between the distances between your snake's head with the other snake's head. That way, the map size doesn't really matter, right? Feel free to explore. The second method that you could change is you can play with the neural network configuration. For anyone who has done this, there are a billion parameters that you can tune. Go ahead. So thirdly, okay, this is what I am the most excited about, is the rewards design. So right now, the gym that we did only accounts for, where is it? Surviving another turn. Right now, you can actually select a whole lot of different rewards that you can take. Maybe, let's just say, all you care about is your snake eating other snakes, and that's how you're going to win. So you would just put a reward for this. Or you want to take an extremely defensive snake. So you would just say, don't get eaten by another snake. Oh, I didn't write that down. But don't get eaten by another snake. That could be another possibility. Okay, so next part is, I'll just give a bit of technical detail about the module. So we built it on Apache's MXNet, and the solution was built on SageMaker. Has anyone used SageMaker? One person, two, three. Okay, that's good. Good start. Yeah. Okay, so I'll explain a bit about SageMaker. So SageMaker provides methods to build, tune, train, and deploy a model. So the training part is, we know that everyone does not have a 12 gigabyte GPU at home to train Battlesnakes. So we'll allow you to train this on the cloud, and you can actually simply get the snake model and directly deploy it here. Another thing is what is called hyperparameter optimization. So as I mentioned just now, there's so many configurations that you can take. How do you know which configuration is the best? So there are many different configurations that you can see, neural network parameters, environmental configurations. So one example that I took when I was developing the snake was, I found that I was exploring whether or not the borders actually matter. And what I did was I said, okay, one condition was with borders, with the states, one condition without the borders. And then I got a snake that was trained with the borders and without the borders. And then I found that actually the borders made a huge difference. That worked a lot better. So thirdly, once you have a model, you can directly deploy it into the cloud. And my colleague will describe it a bit later. Okay, so I'm going to explain the second module. No, the third module, the heuristics module, right there. So what we try to do for the heuristic module is that we try to provide a starting point for you to build upon. So let's just say if you don't want to necessarily train a snake that uses reinforcement learning, you can use the heuristic module. And we also know that not everyone has or wants to train the AI for days and days. Then you can actually also leverage the model that we train and then just add your own flair to it. So basically, you can override the commands of the AI, given your intuition. So let me give you an example. So let's just say you have a snake configuration like this, and you are the pink snake. And the AI tells you to go left. But, no, yes, left, this way. And you know that if you go left, and this guy goes up, then you're dead. But, so to the AI, maybe this actually seems okay, right? Because it doesn't predict to the future that much. So, but you as a developer, you know, okay, we need to go right in order to survive. Does that make sense? Yeah, it's just sometimes the AI is stupid. Yeah. Okay. Furthermore, we tried to streamline the development process. So the suggested way in Battlesnake is actually, from my understanding, is you put the Battlesnake engine on your computer, then you develop it, then you upload it onto the cloud, then it plays Battlesnake. Is that, yeah?
Just to understand,
yeah, I read the FAQs. Yeah. Maybe I'm the only one. Yeah. So what we did was we actually have, I developed the gym, right? I spent so much time on it. Why don't we could just use this to do the development. So actually you don't need to install the engine, like the complicated engine or whatnot. You can just use the gym, which is just a few lines of Python code. And then once you develop this, you can push it onto the cloud. Okay, so the third component of the heuristic module is what I call the situation simulator. Yeah?
Sorry, just to clarify, so did you re-implement the game engine in a gym environment?
Yes.
Oh, okay, wow.
Yeah.
Sweet.
Yeah, they took our engine and then made it work inside of the gym framework.
So does it wrap the engine or
No, it's a rebuild.
Oh,
So
okay.
Yeah,
it is a
yeah.
little out of date
Are you
now,
sharing
but
that? Yeah.
roughly right.
I read source code. Yeah.
And are you planning on sharing that?
Yeah.
Awesome.
We're gonna share it.
That's sweet. Thank you.
No, you're welcome. Okay, so the third part is the situation simulator. So what I did here was, okay, we said, let's just say you have you want to know exactly what will happen if there are snakes in this configuration, and what will your snake do. So what we did was you can define where the positions of each one of these snakes are, and then just test it to see what your snake will do. I guess that's not an option in the
Not at the moment.
Yes. Thought of something useful, yeah. So you can put the situation, you can put these, the configuration directly into the gym, then you can simulate it with the heuristic module. Okay, so I'm done. So the AWS stuff is
Yeah, thank you, John. So, yeah, going back to the one-click deployment with SageMaker, so the action I launched before. So, yeah, once you use the single-click deployment, you have the whole environment deployed. You can train the model, write your custom rules from within the environment we built, and using the existing train we have. So the three modules, okay? And the architecture we deploy, so we go back to the browser to make sure that it works, and we have everything deployed. So it looks like that. So everything is deployed through AWS Cloud Formation, what I showed before. It's just the service that spin up the architecture. The architecture, so there is an entry point for the Battlesnake game to connect to the AI, like for any participant to the Battlesnake tournament. This entry point is provided by Amazon API Gateway, which is an HTTP REST API gateway. It has to put in front on some compute solution. Here, there is a translation system built on AWS Lambda that creates a mapping between the expected API of Battlesnake and the representation that SageMaker and the AI have. So the Lambda here makes a transformation between the game state and the representation that the model needs, and the same when the answer comes, it comes with number like 0, 1, 2, 3, Instead of up, left, right, down, you make a transformation, you return a JSON as an appropriate format to make it work. And so the lambda every time we call a SageMaker endpoint instance that contains two things. It contains the AI model, so the neural network, and on top of that, it runs a heuristic implementation that you write. So by default, we provide a heuristic implementation that we try to go to eat food and avoid wolves.
No, the neural network does have
Yeah, so we put some rules to show you how to make it working. But for those interested in the module 3, you can customize from the environment, you can customize this Python file and change the heuristic you want to put in place. And you can do that through an Amazon SageMaker notebook. So a notebook is a Jupyter notebook. So Jupyter is an open source framework for AI and data scientists. So it shares documentation and code in the same place. And we've built an environment with explanation how to tune that and how to access this file. And you can live change your implementation. You will do your deployment, and then you can call your snake and your snake behavior change. Or if you want to go further and you want to retrain the snake, then you will use the Amazon SageMaker training instance that will run for a duration that you define, or a stop criteria that you define, where you want to stop when you think that your snake are good enough. You will optimize some, like the X, you want it to minimize. You say, okay, when I'm here, I'm done. So everything will be deployed by the transformation script. So I will be switching to the to my browser to look at how it has been deployed. Okay. So here on this page, in my mouse, I will just refresh here. Okay, here it looks like that's good, and here there's also refresh button. Yeah, create complete. So the whole stack is in create complete state. That means that the execution of the deployment of the architecture we just saw is done. And so there are several tabs here in this window. One of the tabs is outputs. So outputs are some outputs that we've defined in the CloudFormation template, and we've defined, okay, we'll provide you a link to the start method to make sure that the snake is working. This is the entry point to the API gateway. Okay, this is what you need to put in the game. The snake endpoint is the endpoint where you can do the move, start, all the API calls. So there is move, start, ping, and end. And a link to the training environment for the customization. So first I will check that I will click on that link to make sure that the endpoint is available. So I opened in another tab. Okay, so I just increase. So here I just call the method start, and the method start from the game is the first call that the game engine makes against your AI, and you just return the color you want your snake to have, your head type, and your tail type. Okay. So these are the default parameters, and when you create it, remember there is a way to change that if you want to have a custom appearance. Okay, so that's working. Now I'm going back here. So there is a training environment, and there is the snake endpoint. So what I'd like to do is I will first show you within SageMaker what has been deployed. So here I open in another tab. Just to keep that one. Yeah? Yeah. So yeah, because today the GitHub repo is not public yet, ourselves we can't automatically clone it on the machine. So that's why I want to check here that everything is deployed. So the notebook instance is where all your training environment control and the setting of the heuristic will be made. So this instance is deployed and in service. We can connect after, I will show you. And I just want to check, yeah, I just want to check it deploys. Good. Okay, and the inference endpoint is where the it's a SageMaker machine that is running the AI. Okay, so now I'm just going back to my output. So back here. We will just try the snake in the game. So you copy the snake API URL, you copy that, and you go on the Battlesnake platform. Okay, you don't have to install this Battlesnake on your laptop, you can play it on the online on Battlesnake. So just increasing a bit the size. Okay, so inside the platform, you can go to My Snakes, and here I will create a new snake. A snake have a name, so let's say AWS. The snake have a URL, so it's here. You have to pass what we just copied, the entry point. And we're good. We save that. Okay, we have a snake named AWS. And now we can create a game. So I will add AWS. Yeah, this is mine. I add it to the game. And I want to add some random snakes. So let's say 1, 2, 3 snakes.
Okay, anyone snake there?
Okay, create game. Okay, so you see, this is your snake, these are the other snakes. Again, the color and the head have been defined by the call to the start API. So now I have to go a bit down, and yes, I zoom out. Yeah. And I click play. That died already?
Oh.
The other one will die before. Oh.
See what it's doing? It's like just twirling until it just needs a lot less last minute.
Let's see what's up.
Oh.
Yeah, so among the things we will do before the release, we have, so the training environment that Jonathan built provide more food than the real game. Because for the training it was more efficient. So the snake is a bit taking too much risk into avoiding the food. And also the snakes, it was fun to see the snakes learn that if you eat too much food, on the long run, if you want to maximize your life expectation, life duration, you have less chance. So that's why most of the time you avoid food. So, yeah. Question?
Towards the end, were the snakes taking a lot longer to make their decisions? Look like it's going.
That's actually
No, I mean, so the game platform itself, it's when you see it, it's a replay. In fact, the AI are a lot faster than that to play, and it's already done. It's just slowed down for humans.
Yeah, so like the engine runs behind the scenes and it's pinging all the snakes to a maximum of like every 500 milliseconds. Like that's how long you have to respond per turn. But what happened there is like normally the games just run really fast, but likely our engines are getting a little backed up because we're prepping for some migration right now. So when you start seeing it moving like one at a time, that means it's now live with the engine running the game, and the frame rate just starts dropping.
So, did you actually find that you, because I know there's a timeout limit from how long it needs to make the decision. Did you ever get to a point where it took so long to get through the forward pass to make its choice?
Yeah, so we tried various implementation of the model itself, and we had some that were more compute intensive, and that were having timeout problems. But finally, the one who worked the best are running the inference, so that means the execution of the neural network itself. It's very slow. Currently, on a small instance size, it's under 30 milliseconds, so that's pretty slow. Now it's not a problem.
One thing we've added to the game recently is there's tiny numbers on the right-hand side. That actually shows the last ping, the last response time.
Okay.
And one thing you'll see with ML snakes often is they will surge to have like a big response time for a bit, and then suddenly have really slow response times.
Yeah.
We had one like the winner of our Winter Classic Championship. They had a neater snake. Theirs is interesting because you could find out when they've determined that they've won in the future.
Oh, okay.
They will have predicted out their next 10 moves, and their response time is 1 millisecond, and then it goes right to a win.
Yeah.
Yeah, and you can see here, I mean, from the game point of view, you see only the API gateway, But the network traffic is from here to here, from API gateway to Lambda service called SageMaker, SageMaker runs the model, does the answer, transformation, go back, and all this process, if you look here, it's a little bit small, but yeah, it took only 60 milliseconds to do the full loop. So the neural network execution by itself is very short.
Yeah.
Okay.
This is the like inner nerded me showing, but if you ever watch League of Legends or something like that, you see these like big outplay videos. They really like footage from like huge outplays where like a snake is about to win, but then another snake does this crazy move and then like completely changes the situation. You know?
Yeah.
Everyone's cheering.
You'll see that kind of stuff if you come to the tournament in March, especially on the advanced snakes. There's a lot of really interesting stuff that occurs with that. Like that same snake I was talking about in one of our championships. They actually, in their prediction, they wrote it so that their snake was extra showy. So if it knows it's going to win, it will calculate how to come one turn from killing itself, because it will know it won't die, but it'll put itself into a no-win situation just to show off.
So are you finding that it's the ML, like, well, I'm not sure the provenance of the ML snakes, but how are the ML snakes stacking up to the algorithmic snakes?
Traditionally, terribly.
Okay.
Mostly because you need a certain amount of bandwidth to train, and like Jonathan and Xavier explained, the reward model and then the environment simulation, those are really important to get right. Those are two big levers to hone to get it good.
Yeah.
But there's definitely some, I think what I'm finding interesting here is the combination of building your own heuristics on top of this big picture decision making is pretty intriguing.
I have another question about that. Do the ML snakes tend to sort of bias towards whatever snakes they're trained against?
Yes.
Like so that if a totally new snake comes in, they won't be able to do anything.
It might be, yeah, because ultimately all the snakes has the same neural network architecture. So we didn't show here, but if you look at just maybe like 4 of the same snakes playing against each other, you can see that some of them do the same thing. Do we have a?
So then to have a well-performing snake, you need another algorithmic snake as an agent.
Yeah, you can work on that. Yeah, that's something that you can try.
That's cool.
Yeah.
In theory, though, in reinforcement learning theory, it shouldn't matter if there's an optimal policy. Like AlphaGo, for example, played almost exclusively just against itself and still be the world champion.
It really comes down to how you get your rewards correct, and that's where they're explaining the rewards for snake, whether is being long better or not, it depends. Is eating better or not, it depends. Is attack being aggressive or defensive, it depends. So it's whether that snake learns a pattern, and that's how you set it up.
It's also probably related to the space of the opponents. If AlphaGo covered its entire space of possible moves and strategies, then playing against itself is optimal, but if only covered a subset, then it might not be able to cover the complementary opponent.
It does only cover a subset.
One thing I was curious is, when we made an early implementation of this in Chris, we found that our biggest problem at the beginning was stopping it from just going straight through, because in theory that's a local minima, because if it just goes straight through, it's going to not kill itself as quickly as running into a wall. So it just power right through, and then that would be local minima that I was getting for a while. I was curious, did you guys run into any issues with that, or were you able to get it to explore the state space enough?
What do you mean by straight through?
Like it would run straight through the field. So if it started, because if it starts on the one side, the longest path that it can get is just
into the left. Right?
or up and to the left. Yeah, it would go. You would basically find the longest distance it could travel.
Oh, I see.
Before it
So
would
actually,
turn around and stay within the game.
so that is where the epsilon plays.
Yes, so that's what you can explore the state.
That is what they call the exploratory method. So you just give the snakes random actions and you hope that it learns that, okay, I shouldn't go straight through. Yeah.
Yeah, and we were using a different model, but we ended up solving that by adding something very similar to Q1 epsilon. Entropy faster.
Yes.
Are you done? Am I just keep interrupting you with these questions? Are you done your presentation? Oh, okay.
So it's actually question time.
Okay.
Yeah, we are done. Thank you.
Yeah.
More serious technical questions. So you said that these rule-based versus quote-unquote ML. how is that implemented directly? Like, can you combine the two? And if so, is that done in a trivial way? Like, say, just in a situation use rule ways where to switch to ML, or is it, or can you combine those two in a more subtle way?
I mean, if I go back here, so the model runs. The model say maybe left, and then you have your own rules that are if and else statements, or checking things that you know that should be checked, and you can override the decision and say no. Left, you will die in 2 terms. So no, we do that.
Is there a more sophisticated way of putting that into the reinforcement learning that maybe complements like what's going on in that system? Because it seems like it's using that, it could use it as a crutch and mess up in some way the reinforcement learning model, or is that not true?
That's what he just explained.
You could factor it into your reward function, essentially.
Okay.
Like if you know that's a bad action, you could lower the reward function.
There is some behaviors that you may like that are hard to represent in terms of reward function and game state. So sometimes it is more efficient for simple behavior, but that are very quick wins or very strong wins or lose that you implement them on top of the neural network.
Those reward functions can be extremely abstract then. It can be extremely complicated, what a reward function could be.
Yeah, I can, but then it means your network is harder to train. Okay.
Yeah, and just one last thing to mention. So we bring a demo that is running the Snake on Raspberry Pi here, and so these Raspberry Pi are running the game engine. So this one is running the game engine. The AI is running on this one, and here we have a Xbox controller. So if you want to try play against the AI, you're welcome to do so.
So this was the demo that was we ran live at reInvent that these guys nicely invited us to hang out at, and it's entertaining.
Yeah.
And
the Raspberry Pi is capable of doing that forward pass relatively quickly?
Yeah.
The inference?
Yeah. It's a Raspberry Pi 4. I was running it on Raspberry Pi 3. It was a bit short. So I switched for Raspberry Pi 4 and it works well.
Did you have some questions?
Yeah, I just wondering if the heuristic model, can you use it to dynamically like policy switch or model switch between multiple ones? Or is it just kind of on top of the single model?
Oh, that's a good point. No, we didn't think about that.
But it has access to the full state of the game, right?
What do you mean?
It has access to the entire state at that step.
Yes, it does.
So there's no reason you couldn't do it. You could go, oh, we're endgame now, and go flip this variable.
Switch from like aggressive to defensive?
As long as it has memory, right?
No, we didn't do that. I will jot that down. Yeah. Yeah.
I had a question about that. Talking about doing the borders versus, you have the borders versus like just -1 cells everywhere.
Yeah.
I'm wondering how that, when you're modeling the environment and the rules, because it seems to be you had hard rules about you can't cross the border versus just building it into the reinforcement system. Is that a difference?
The algorithm actually learns that it shouldn't go to the wall.
Yeah.
Yeah, that's not heuristics. We just found that if you put the -1s there, it learns better.
Oh, okay.
It's easier to learn, yeah.
Oh, okay. And so if you're doing like the self-driving car, for example, would you like do the ditches as like -1s?
Maybe, I don't know how to do it, but.
In self-driving car, you don't have a programmatic representation of the world, so they're actually looking through sensor data, like a video camera or a LiDAR. They don't have like a 1s and 0s representation of the world, which is part of the problem with self-driving cars.
Yeah, so if you have a simulator, you would use, yeah.
So the model is like the AI part of the self-driving cars is actually finding out that that's a ditch.
Got it, thanks.
So similar vein. You said that it did a lot better when you have -1s for your borders. I'm just wondering if actually might have been a better idea to do something like take the distance from the center, because it makes sense that -1s would have given a better result because you're incorporating the idea of being close to the edge, which is a danger zone. But when you take that out, every single square sort of seems like it's the same sort of positioning, but in reality it's not. Right? Like,
you should keep it a secret.
Yeah. But maybe, the option for your state representation, reward, and everything is super open. And that's where the secret sauce is in your success. And especially because it's a competition, there is a lot of creativity in that. So just here, I run the demo. I run into the wall to let the two AI playing. So this is twice the same AI that is running. So the two AI are running on this Raspberry Pi, this one. And you see they are, most of the time, they try to avoid food a bit. And here the game is tweaked a bit to provide a bit more food. This is where the AI are a bit trained. So it try to maximize its life duration.
So you can actually see, maybe answering the question before, the behavior is kind of similar. Yeah. So did you have?
Yeah, my question was when you were talking about dealing with like n by n board spaces and how you manage that. What were some of like the solutions that you came up with, like a radial around the head or like and stuff like that?
Our solution right now is I just trained it 5 times. Yeah.
Okay.
Yeah. Definitely. I have a model for 7 by 7, 11 by 11, 15 by 15.
Just for like dealing with like the bounty kind of situations, right?
Yeah.
Like, some bounties were like 50 by 50, like every space was food.
Pardon me?
Like last year, like one of those situations was like a 50 by 50 board, but like every tile is food. So just like how would that be imported into like
I'll say
n by n?
Yeah. See, for like if you're competing in bounty snakes for this year and you're going to try to use this, you likely, if they're really weird, you would have to train for that new environment and whatever. And like they showed the representation of the environment, you may have to change what that representation is, which is a whole retrain as well.
Yeah.
So in this case, this might not be your way to go after bounty snakes, unless they're following at least something in the standard pattern of the game. Otherwise, it's the weird environment is going to be like, oh hey, we just threw a snake down, it has no space helmet in the vacuum, like it's just going to die, right? It doesn't know how to deal with that weird space.
One way to handle that, because I remember there was variable board size when we were doing this, and it was like putting a moving window on the head of the snake. So just kind of, then you can basically make a train on kind of a sight box.
Yeah.
Again, it's just going to be kind of hard to see how that works out, right? Because you're trying to be overly general, so you're probably not going to be able to train it with a fixed board size, the same effectiveness. So it's going to having to account for that's just going to reduce accuracy.
Thank you.
On the other hand, I think that could be interesting, and I'm curious what you think, because you're representing like your current snake as it could be anywhere on the board. So the model has to learn all these different positions that its own snake could be in. Where when we had our window, we always orientated it so that the snake's head was facing up and in the center of the window. So it led to like the model only had to learn so many situations because there's a more limited set of possible situations that it could be in. I'd be interested in hearing your thoughts on that.
Yeah, we actually thought about doing it that way as well, just actually as an option for the hyperparameter optimization. Never got around to it because like the map size is a big issue, but possibly I'm not sure which one will work better. We never tried it.
So there's a solution to that in that you use a larger image. So if you're training on like an 11 by 11, you can use say like a 22 by 22. And then as an extra layer to your input, you encode the game area as black as like a max value for those pixels.
Yeah,
and that works for training various size boards. Like I've done recently.
Or just like the -1 borders, right? You just make it bigger. That's a possibility. Never tried it, but feel free. Yeah.
Maybe because I don't understand the rules, can you explain the intuition why snakes should avoid food? Like why won't we eat as much as possible? It'll be a big snake and I can eat other snakes.
So actually that is what the algorithm learned on its own.
Is it because it's already incompetent and it just runs into itself?
No, I think it's because the reward's set on length of life.
Yeah.
So when you do that, the algorithm thinks it's better to play a longer game, even if it's a boring one when they both kind of avoid each other for a long time. That is scored higher than pinning the other snake and finishing the game.
So you ended the game by winning. That's how you.
No, but the reward is just incrementing one more reward every step. So the reward doesn't know that you're winning or losing. It knows that you're living for longer. So you've emphasized long games and avoiding a quicker solution. But that's entirely in how you set the scoring up. So in other words, it learned that because of the way that he taught it what a good thing was. If you change what a good thing is, for example, if you made it 150, one to live, but 150 to eat another snake, it would start chasing snakes around.
But
it wouldn't always work.
Okay, I don't want to jump in too much because that's a really interesting conversation about reward shaping, but I see some people are looking a little eager. So we still got the space for like 20 minutes. So I want to say that like we can hang out and chat and lots of questions still. Like I know I have some. So feel free to hang around, but also if you got to go somewhere, feel free to do that. So I just want to make sure that while we're all here, we thank the speakers one more time. So thank you both.
And if some of you want to try to play, they're welcome.
It's harder than you think.
I think I know two days here. So.